Hello everyone, I'm Daisuke Mashima from ADSC. So in this presentation, I'll talk about a project focused on design and enhancement of smart grid honeypot system. So this is a joint project with my ADSC colleagues as well as a cybersecurity expert from Custodio Technologies in Singapore. So as you may all know, so Honeypot is an effective tool to collect intelligence about the real-world cyber attackers and malware. By using the collected information, we can fine-tune the cybersecurity measures such as antivirus software, firewall, and intrusion detection systems. And for these purposes, Honeypot has been long used in the cybersecurity domain. However, Honeypot for the smart grid system is still in the early stage. Specifically, we do not see the implementation of the Honeypot that emulates the whole infrastructure of the smart grid system with a sufficient cyber-physical fidelity. Also, we do not have an established methodology for evaluating the goodness of the Honeypot system. So in this project, we particularly focused on these two challenges. Let me first go through our approach. So we start with developing the prototype of the Honeypot system that emulates a typical smart grid infrastructure. So then we evaluate this initial prototype from the attacker's perspective by means of a penetration testing. Then, based on the finding, we improve the Honeypot implementation to be ready for the real-world threat intelligence collection. Actually, this step 2 and 3 are repeated multiple times to iteratively improve the quality of the Honeypot. Let me next explain the initial Honeypot design and implementation. So we studied substation and smart grid systems that are compliant with state-of-the-art IEC standards, such as the IEC 60870 and 61850. And then we designed the Honeypot infrastructure like this. And it consists of a virtual control center network as well as a virtual substation network, which are connected by a virtual wide area network. And the control center network hosts, for example, SCADA HMI workstation and a historian database, and VPN server for the remote access, and firewalls facing the external network as well as the wide area network. In the substation, there are VPN server for the remote maintenance or remote access, and also smart grid devices such as the substation gateway and IEDs, intelligent electronic devices. And also we have a firewalls facing wide area network as well as the external network. So we think this is a typical setup that many researchers would start with. So then next step is to evaluate from the attacker's perspective. So to do that, we designed a penetration testing by a cybersecurity expert. So we first developed the attack scenarios based on the ones discussed by the ICS CERT and ICS Cyber Chain. So our attack scenarios consist of roughly 2 phases. So in the first phase, a remote attacker may aim at compromising a VPN interface on the control center network and or the substation network to have a footprint in the system. So after successfully penetrating into the system, the next step for the attacker is to collect the information in the system by enumerating the devices or services running there. So then next phase, attacker's goal is to inject a malicious control command into the smart grid devices, in particular IEDs. So IEDs are basically the communication endpoint in the cyber side, and they are connected to the physical power grid component. And the attacker may be injecting a malicious command via SCADA HMI workstation, just like the Ukraine power plant attack in 2015, or attacker may directly inject a command to the substation system. So to emulate these kind of attack scenarios, we utilize the widely used cybersecurity tools such as Nmap and Metasploit. So then, through the experiment, we identified a couple of issues we need to improve. First one is the presence of the virtual machines hinted by the network open ports. So to address this, we close the related ports after all the virtual machines are started. The second issue is a lack of live user account on the Windows machines. So like attackers sometimes exploit the existing user accounts to compromise a server. So in this direction, we prepared a dummy user account with a popular user ID such as admin and weak password. The third issue is, our virtual implementation of the smart grid devices exhibited a totally different OSN device fingerprint when they are scanned by the Nmap kind of tool. So we will discuss a solution to this issue in the next slide. So when considering a countermeasure against the OS fingerprinting, we categorize the devices into two types, or smart grid devices into two types. One is a passive device, which only acts as a server in a TCP or UDP. The other category is an active device, which also works as a client. For example, in IED belongs to the passive device category, while the substation gateway or PLC belong to the active device. For example, gateway acts as a server for the SCADA HMI workstation. On the other hand, it works as a client towards the IED in the substation. So to deceive a device fingerprinting tool, we first consider imitating the network characteristic. So in this direction, we study the real devices deployed in a smart grid testbed in Singapore, and we deploy the same set of network services on the virtual IED. And also we assign the MAC address that belongs to the same company as the real device. Then to deceive the OS fingerprinting tool such as Nmap, maybe radical solution is to change a protocol stack implementation of the OS, but it is not often feasible. So in this direction, to find a feasible solution, we employ the open source software called Honeypot, which has a capability to deceive a device fingerprinting. So then we put the Honeypot as a front end facing the network, meaning all the accesses to the HTTP server or IEC 61850 service are proxied by the Honeypot. This way, so we can effectively deceive the device fingerprinting tool. We also have a dummy traffic generator for the better realism. Regarding the active devices, we first did the same thing. Say we run the same set of network services, in this case, HTTP, IEC 6870, and SSH. And also we copy the MAC address from the real device. But to deceive device fingerprinting, for active devices, Honeypot alone is not sufficient. So because outgoing traffic is not supported by the Honeypot, so we cannot deceive a passive fingerprinting tool. But on the other hand, good thing is that say gateway or PLC, many of the active devices run on Linux type operating system. So based on this observation, we decided to use a small virtual machine to emulate these devices, and we run the similar version of the Linux OS on these virtual machines. And another important feature is logging on the Honeypot system. So purpose of the Honeypot is to capture the attacker's behavior. So we need to implement logging in a secure and tamper-resistant way. So to do that, we deployed a number of so-called transparent proxy boxes throughout the Honeypot infrastructure. So transparent proxy is a sort of bump in the wire device that can transparently monitor the network traffic. So because these boxes are not addressable by the attacker cannot compromise such a logging. Also, we have implemented application level logging at the virtual IED and PLC, and also substation gateway. The way we implemented these logging securely, so we provided more detailed information on the paper. So this is the architecture of the improved Honeypot. And as can be seen, we have deployed a number of transparent proxy in a Honeypot system, as well as application level logging. The information collected from the application level logging is found in this table. So then let us move on to the evaluation about countermeasure against the OS fingerprinting. So we actually did a fingerprinting using Nmap against our virtual IED, which is shown on the top, and real IED. And we also show the result of the fingerprinting of the original IED implementation. So as can be seen, initial IED implementation shows a totally different fingerprint compared to the real IED. On the other hand, the real IED and our improved IED shows very similar fingerprints. But still, there are some differences, as you can see. However, so the SP, ISR, and SS, these numbers are changes for each scanning. So meaning that the value fluctuates within a certain range. So it is not a critical factor to differentiate in virtual IED from a real IED. So one consistent difference may be seen in a value called IPL. But this IPL value is different for each model of the smart grid devices. Say certain model of the IED may have to 240 as shown here, but another type of smart grid device has 164 actually. And there may be some other devices with a different number. So in this sense, without a very detailed, complete knowledge about the exact model of the device deployed in a target infrastructure, attacker cannot tell based on the IPO whether this device is fake or real. So regarding the OS fingerprinting of the active devices, we attempted Nmap as well as the P0F, which is a passive OS fingerprinting tool. So for the result with Nmap, we do not see significant difference. And regarding the P0F fingerprinting result, we see difference in message segment, maximum segment size element, but this number changes over the changes depending on the network link. So it is not, again, a critical differentiating factor. Okay, so let me conclude our presentation. So in this project, we designed and implemented a Honeypot that emulates a comprehensive smart grid infrastructure. And we presented the evaluation and enhancement procedure by using a penetration testing. And we published the outcome of the project, including the virtual machine images on our website. So regarding the future work, we plan to conduct further evaluation with more participants. For example, by means of a capture the flag hacking competition. We will also deploy the improved Honeypot system for actual data collection with a realistic company's IP address. And finally, we plan to explore the use of this Honeypot as a venue for the education and training. So thank you very much. That's it for my presentation.